Swayam Prabha. Digital India. Educated India.
Now let's look at this even further. Let's go a little bit more into depth here. Now suppose now what is this particular expression here on the left? What is this particular expression? The infimum of this linear function evaluated over t. Now if you recall, I had discussed this a little bit earlier, right? If you evaluate a linear function over g, right, and when lambda is greater than or equal to 0, okay, all right, and when this quantity here is 1, right, then that linear function was actually nothing but the minimizing that linear function was actually the same. The minimizing that linear function was actually the same as minimizing the Lagrangian over the entire space. So its value was actually the value of your dual function. So now I want to try and relate this in that way. So what I have on my if you just take this here, so I have infimum of, let's write this out here once again. So infimum of lambda tilde transpose u plus theta tilde transpose v plus mu tilde into t over u v t in g. This is greater than or equal to for us mu tilde into p star. This is where we had reached. Okay. Now suppose, just suppose, or you can say let us take two cases. Okay. So case 1, is when, okay, so actually so now in fact before I take these two cases, let's look at this once more. So what we have done is we have said that, well, T and G, okay, they are convex sets, and we applied the separating hyperplane theorem, and that has got us to this stage, that has got us to this particular inequality here. Okay. So now we have so far, what have we assumed about the optimization problem? We have assumed that, well, you have this optimization problem where A is full row rank, GIs are convex, and this is attained. And from there we said we only showed that, well, G must be a convex set, T must be a convex set, G and T are and we said that there must be a separating hyperplane that separates G and T. I have not yet made any assumption about constraint qualifications. Okay, so now what I will do is I will actually introduce a constraint qualification. Okay. So what I will do is, okay, so we've reached this stage. Okay, so now before we move any further, so let me erase this. Before I move any further, now suppose okay, so this is going to be my theorem. Consider the convex optimization above, convex optimization problem So, A is P cross N, rank of A is P, and suppose there exists an X hat such that, so we want a Slater point, right. So, there exists an X hat such that all these Gi of X hat is strictly less than 0 and Ax hat is equal to B. Okay. So, this sort of point is what is called a Slater point. Okay. So, consider the convex optimization this, and suppose there exists an X hat such that Gi of X hat is strictly less than 0 for all I from 1 to m and Ax hat is equal to B. Okay. So, this is what is called a, suppose there exists a Slater point and this condition is what is called a Slater condition. Okay. Then P star is equal to D star, and what is D star? D star is simply the max of D of lambda comma theta over lambda greater than equal to 0. So, it is the, so at P star, so the optimal value of the primal is equal to the optimal value of the dual. Okay. So, that is what we are setting up to show. So, we came up till this stage. We wrote this set, we wrote this set G, we wrote this set T, and we found that these two sets are disjoint, and then therefore, there is a separating hyperplane, and the separating hyperplane gave us that that there exists this sort of quantities lambda tilde, mu tilde, etc., such that lambda tilde is greater than equal to 0, mu tilde is greater than equal to 0, and this inequality holds. Now, from here onwards, I will have to invoke my Slater, I will have to invoke that we have a Slater point. Okay. So, now suppose here, okay, suppose out here mu tilde is positive. Okay. Now, suppose mu tilde is positive, or let us say we are taking the case where mu tilde is positive. So, if mu tilde is positive, then what can I do with this expression? This expression, let me just write this expression once again there on the next slide. So, I have this expression infimum over u v t in G lambda tilde transpose u plus theta tilde transpose v plus mu tilde times t. This is greater than equal to mu tilde times p star. That is what we have so far. Now, suppose mu tilde is positive, and I have that lambda tilde is greater than equal to 0 already. So, this is actually nothing but the infimum, this is nothing but the infimum of the Lagrangian evaluated at so what I can do is the following. So, if mu tilde is greater than 0, I can just divide all sides by mu tilde, and then I would get that this is nothing but the infimum of the Lagrangian evaluated at lambda tilde divided by mu tilde and theta tilde divided by mu tilde, and that would be greater than equal to p star. And what is this infimum? How did I get this? This is because of what we just wrote here, that we wrote that the dual function is actually equal to the infimum of a linear when lambda is greater than equal to 0 and this coefficient here is 1. The dual function is actually equal to the minimum of this linear function over this entire set, over this set G. And if you see, that is exactly what this was. This was the minimum of this linear function over the set G. Lambda tilde was greater than equal to 0. We didn't have a coefficient 1 here, but that coefficient can be made 1 by just dividing throughout by mu tilde, and that you can do because mu tilde is actually we assume mu tilde is greater than 0. So, when mu tilde is greater than 0, this becomes the infimum of the Lagrangian, which is simply d of lambda tilde divided by mu tilde, theta tilde divided by mu tilde, and that is greater than or equal to p star. And what does that mean? What does this? This means that this means that we have got the inequality which is opposite of that of weak duality. So, which means this implies strong duality holds. Equivalently, d star equals p star. So, when mu tilde is positive, effectively what we have done is we have automatically found a non-vertical supporting hyperplane, and that has given us this particular direction. Now, for the when mu tilde is, now suppose mu tilde is equal to 0. See, mu tilde is greater than or equal to 0. We took care of one case where mu tilde was strictly positive, and there we got that strong duality holds. Now, when mu tilde is equal to 0, there should be, we should be able to rule out that, we should be able to still show that, either still show that strong duality holds or rule out that this case is not possible. Okay. Still, until this point we have not yet made use of the Slater condition. We have only used convexity. So, now we are going to need this, we are actually going to need Slater condition. Okay. So, let us look at it this way. So, now suppose mu tilde is equal to 0, then what happens to my right hand side? My right hand side here becomes equal to 0 when mu tilde is equal to 0. Okay. So, if my right hand side is equal to 0, then I am left with, and on the left hand side my mu tilde times t, that term is also equal to 0. So, when mu tilde is equal to 0, what I am left with is something like this: lambda tilde transpose u plus theta tilde transpose v, infimum of this over u v t belonging to G. Now, this here I can again, since lambda tilde is greater than or equal to 0 and v should be equal to ax minus b because of u v t belonging to G, this in fact can be written in this way: infimum of lambda tilde times this itself. So, the least value of u will be attained when u is actually equal to g of x. So, it is infimum of this into lambda tilde transpose g of x plus theta tilde transpose ax minus b, okay, and over all, the infimum is over all x. Okay. Now, let us take x to be a Slater point. Okay. So, suppose suppose when, okay, sorry, this is equal to this, and my right hand side on the other hand is that my right hand side here, remember this quantity evaluates to 0. So, this whole quantity is, what I get is that this whole quantity is greater than or equal to 0. In other words, I am getting that lambda tilde transpose g of x plus theta tilde transpose ax minus b is greater than or equal to 0 for all x. Now take x equal to x hat, which was my Slater point. Okay. So, I had this x hat here, which was my Slater point. So, let us take x equal to x hat. So, what would we get from there? We would get that g of x hat, remember, would be strictly negative and ax hat would be equal to b, right. So, if gi of x hat is strictly negative and ax hat would be equal to b and ax hat is equal to b. So, if I put x as the Slater point, that would imply that the only way possible is, so that would give me, so here the tilde. So, lambda tilde g of x hat greater than or equal to 0, and the only way that is possible is that lambda tilde is equal to 0. So, not only is mu tilde equal to 0, I have now also got lambda tilde is equal to 0. alright. We are now almost at the end. So, if mu tilde is equal to 0, lambda tilde is equal to 0, the only way, remember the separating hyperplane theorem told us that there is a non-zero. What did the separating hyperplane theorem tell us? That it told us this should be non-zero, right. So, the only way this slope should be non-zero is that theta tilde is not equal to 0, write this more neatly. So, the only way that is possible is that theta tilde is not 0. Now, theta tilde is not 0. So, let us what does this mean? But anyway, we have got that lambda tilde is equal to 0. So, this term is now gone. It means now that with theta tilde not equal to 0, we must have that this expression is greater than equal to 0 for all x. Okay, so let's go back there. So, which means that theta tilde transpose Ax minus b is greater than equal to 0 for all x. Okay. Now, if you take so let's think about it this way. So, here is Ax minus b, okay, at x equal to x hat, okay, at x equal to x hat, which you have Ax equals b. Now, that means that is a point that is exactly on the intersection of all of these hyperplanes, right. So, in the neighborhood of this point, you should be able to find there exist other points where you should be able to find other points for which, for whatever slope you take, you should be able to find points for which the inequality actually gets reversed. See, it's this quantity is great in a neighborhood of this data point. There would exist points like this, points where this inequality gets reversed, unless, see, because this is after all a linear function. This is a linear function. So, at x equal to x hat, the left hand side is becoming exactly 0. So, you should be able to find other points where in the neighborhood of x hat where it also becomes negative, right, because this is a linear scalar function. So, since it is the only way it is not that a linear that this function will not become negative is that its slope is actually 0. Okay. At x equal to x hat, you have Ax hat equals b and LHS equals 0. In the neighborhood of x hat, we have that there exists x such that theta tilde transpose Ax minus b is less than 0, unless it's the slope itself is 0, unless theta tilde transpose A is equal to 0. Now, so in that case, then you will not be able to change x and get to a you will not be able to vary x and get to a negative value. So unless it is a constant function, the linear function around that point would take values that are both positive and negative. So now and it will be a constant function only if the coefficient itself is 0. But then can this coefficient actually be 0? What is this actually saying? Well, for this coefficient to become equal to 0, what we are saying is that theta tilde transpose A is equal to 0, which means that if you take the rows of A and you sum them up using some linear combination, which is with these non-zero weights, with a bunch of weights that are not all 0. Okay, so you take a linear. So this is actually the left hand side is a linear combination of rows of A, and that linear combination we are saying is equal to 0. Well, that means that, what does this mean? That means that the rows of A are linearly dependent. Now, but then we if you recall here, what did we just assume? We assumed that the rank of A is equal to P. That means it has full row rank, which is a contradiction to that. Contradiction, since A has full row rank. So, the only way this is possible is that that A has linearly dependent rows, but we assume that A is full row rank. So, the problem we are starting with is one where A has full row rank. So, which means that this is also not possible. Okay. So, what does this mean? What this has got us to is that this case, right, this case here where we said suppose mu is equal to 0, this case is not possible. So, which means mu tilde is not equal to 0, which means the only case, that is mu tilde has to be greater than 0, right, and is the only possible case. And then, which means that strong duality holds. Okay. So, the only possible case is this case where mu tilde is positive, and in that case we concluded that strong duality holds, and that is the proof. So, to summarize, we have a convex optimization problem as written here with the following requirements, that the constraints, the linear constraints have are full row rank, and there exists a Slater point for the constraints, right. You put these together, then it has to be that the optimal value of the primal is equal to the optimal value of the dual. That is what this theorem has shown. Okay. And in proving this, basically up to the point we got to the point where we wrote this set G, we wrote this set T, we showed that the sets T and G are both convex, and then we showed that there must be a separating hyperplane. Now, the problem from there onwards was that we wanted to show that the existence of a non-vertical separating hyperplane, which means that we wanted that this mu tilde is not the mu tilde here has to be basically positive, okay, and that this slope here is greater than equal to 0. The greater than equal to 0 came quite easily, but in showing that the separating hyperplane is non-vertical, that means this mu tilde has to be positive. That's where we needed a constraint qualification. So until that point, everything works without constraint qualifications. The constraint qualification ensures that your slope is that your separating hyperplane is actually a non-vertical one, and that is what actually makes your strong duality work. Okay. So, with this, then we have now shown strong duality also for convex optimization. You will recall that the Slater condition, which is the constraint qualification for ensuring strong duality, that condition was also what gave us was also used in KKT conditions. So, all these things come together when you actually solve an optimal when strong duality holds, the optimal values of these Lagrange multipliers are also optimal values of your also what will the optimal values of the dual variables are also what will solve your KKT conditions as Lagrange multipliers. Okay. So, this so with this I will end here, we will next move on to a new topic.